Hello everyone, my name is Shabani. I am a PhD student at the University of Basel. Today I will present our work titled Hybrid Human-Machine Classification System for Cultural Heritage Data. This work is done under supervision of Professors Heiko Schuldt from University of Basel and Maria Sokhn from University of Applied Sciences, Western Switzerland. In our daily life, we come across digitized historical content which is very important for cultural heritage domain. Very often, these historical data have issues of incompleteness and inaccuracy. For instance, images miss the spatiotemporal information, when or where the image was taken. Moreover, many historical datasets are poorly annotated, as images may be missing tags and are not categorized. The goal is to complete the metadata of existing digital collections, but also to enrich with new content. The focus of our work here is to add a new attribute to the metadata named cultural interest by categorizing the images into 5 predefined categories if the image is talking about a place, person, object, event, and/or tradition. Adding this new attribute is beneficial for structuring and searching purposes. The outline of this presentation is as follows. I will introduce the idea behind this image categorization task and the expected goals, and later describe the dataset. Then I will present the proposed hybrid human-machine image categorization approach by describing individually the deep learning method, crowdsourcing, and the hybrid framework. Finally, I will summarize the presentation and list the future work. Citizens and cultural heritage institutions have crucial roles to play for transferring historical information between generations and civilizations. Many citizens own valuable data, such as photo albums or audio and video archives, that can be of great public interest. Considering the advances of internet technology, many cultural heritage organizations like galleries, libraries, archives, and museums motivate digitizing and sharing their collections via online platforms. These platforms are used for documentation and management of historical data collections, generating metadata that are very important. However, obtaining complete metadata is very challenging. As a result, many historical datasets are poorly annotated. In our City Stories project, we address these issues by leveraging the human intelligence to correct and fill missing information, but also to share new content. Additionally, we consider enriching the metadata with new attribute named cultural interest. The objective is to categorize all images in one or more of the 5 categories: place, person, object, event, and/or tradition. As the amount of digitized collections increases rapidly, adding this information is very helpful when structuring and searching for data. For categorizing the images, we implement and evaluate 3 methods: automatic categorization with machine learning and deep learning techniques, worker profile-based crowdsourcing, and hybrid human-machine approach, which combines machine learning and crowdsourcing. The dataset we used in this work was taken from Notre-Histoire, which is a participatory platform for sharing and valorizing the history and cultural heritage of different regions of Switzerland. Notre-Histoire invites volunteers to publish and share their own digitized archives, along with institutions. The platform has collected more than 100,000 documents, mainly images. Since our goal is to add a new information to the metadata, the dataset was not labeled, so ground truth data was needed in order to evaluate our approaches. Therefore, we selected a sample of 5,015 images and invited 10 participants from the region to help annotating the images. To participants were presented the idea behind the project and comprehensive examples on how to annotate the images. In 2 rounds, the 10 trained participants annotated the images. In the first round, they used a pooling mechanism where each annotator was assigned an image not annotated before. In the second round, annotators were assigned images that had already been annotated by others from the first round. Inter-rater agreement was 0.55, and considering this is a multi-label classification task with 5 classes, this number can be considered substantial. Another extra round was used to resolve the disagreements. For the annotation, we developed a web application which included game design elements such as a leaderboard and badges. Table 1 represents the number of images that contain each of the 5 categories. Clearly, most frequent category is place, followed by object and person. The less represented categories are event and tradition. Since this is a multi-label task, we looked at the distribution of categories. Table 2 shows the number of categories per image. 67% of images have single category, about 30% have 2 categories, and about 2.5% 3 categories. Only 2 images were assigned 4 categories, and none of them had 5 categories assigned. We initially evaluated automatic image categorization using machine learning and deep learning techniques. In parallel to considering the visual features, our approach utilizes the existing available text information in the metadata, such as title and description. Moreover, our method follows a process of adding more text information with the final goal of adding more context, so models can perform with better accuracy. We follow a 3-steps process to do this. First, we use VGG pre-trained model to obtain general classes from the image and join these classes with the available text in the metadata with title, description, and user-provided tags. Then we use DPpedia Spotlight entity extraction tool to extract concepts linked to Wikipedia knowledge base. Finally, for each Wikipedia concept, we use DPpedia endpoint to retrieve the categories and their properties of these concepts. Our assumption is that DPpedia categories can provide more specific information that connect directly with the image category we aim to predict. This is better illustrated in this figure. The example image is taken from during the Geneva Festival. The pre-trained VGG model provides the text, marching band, and parade uniform in English. The entity extraction tool recognizes the concepts Fête du Genève and fanfare, marching band, and parade. Exploring the DPpedia category of the Fête du Genève concept gives us the Fête Suisse, which is another event. On the other hand, categories marching band and parade give more context that this event is a tradition as well. Initially, we evaluate the accuracy of the machine learning models by considering only textual features. Feature extraction is done with TF-IDF algorithm. To analyze the importance of the generated features, we run the evaluation of the model separately based on different settings. We tested 4 combinations, in each step adding more text information. While the accuracy of the 3 chosen models are similar, the SVM achieved the highest strict accuracy of 58%. Our initial assumptions that adding more information will boost the accuracy were valid, and this can be observed from the results shown in Table 4. Adding VGG classes, Wikipedia concepts, and their categories improved the accuracy by 7%, from 51 to 58%. Our next step was to evaluate the performance of a deep learning multi-input model that combines text and image features. Considering that our dataset consists of 5,015 samples, the size of this collection would not be enough to build and train a deep learning model from scratch. Therefore, we apply transfer learning techniques by using a word embeddings layer with weights from blob model and MobileNet pre-trained model. MobileNet model was set to use weights from ImageNet, which is trained on a large image collection and with a more general classification task. A new classifier with our custom dataset labels on top of it was added and trained with images from the training set. Figure 5 outlines the training and validation accuracy score of the multi-input deep learning approach. After 30 epochs, our model achieved an accuracy of 63% and Hamming loss of 10% on the validation set. It is important to emphasize the effect that the transfer learning method has on the model's accuracy. During the first 10 epochs of the training and the validation process, we set the layers of the mobile net pre-trained model as non-trainable, frozen. After that, the last 100 layers out of 155 were unfrozen and we retrained for another 20 epochs. We can observe that the accuracy increases as an effect of transfer learning. This is shown in the image after the yellow vertical line. Finally, we evaluated the model on the testing set and accuracy achieved was 62%. Considering the potential of deep learning, and on the other hand, that the limitation of the small data and the time-consuming annotation process, as a result, we considered crowdsourcing as an alternative solution to this image categorization problem. We chose the microworkers crowdsourcing platform to deploy this job by generating 5,015 human intelligent tasks, one per image. One of the main issues in crowdsourcing is the data quality. Therefore, in order to reduce this risk, we considered quality control mechanisms such as test questions, reputation of workers by selecting the highly ranked crowd workers, and redundancy by asking the 3 crowd workers to annotate the same task. Redundancy could have counter effect considering that this is a multi-label classification task. However, we further consider aggregation techniques when selecting the final answer. It took 8 effective hours for the annotation to be completed, where 542 users from 78 countries participated. Since the images we used in this data set are specifically about the Swiss regions, we provided guidelines and comprehensive examples so that crowd users from different countries get more information about the annotation rules. As mentioned previously, the image categorization is a multi-label task. Therefore, having multiple judgments can lead to higher disagreement between annotators, which yields to low-quality answers. To tackle this issue, we implement and evaluate 3 answer aggregation methods. First, we consider majority voting algorithm, which simply select as final the answer given by the majority of workers. Next, we evaluate the David and Skinny model, which is based on the expectation maximization principle to model the workers' reliability with a confusion matrix for the answer aggregation. Last, we apply a truth inference algorithm that considers prior information provided by the crowdsourcing platform about workers' profile. We derive a reputation of a worker based on his previous finished tasks, such as number of accepted and rejected tasks, money and badges earned, and integrate that score in a weighted aggregation method to infer the true answer. Our assumption that in a multi-label task, redundancy can lead to higher disagreement were confirmed. If we simply aggregate the answers without any quality control mechanism, adding the responses from the second and third annotator reduced the accuracy from 49 to 41%. The majority voting achieves an accuracy of 56% and Hamming loss of 12%. The David Skinny and worker profile model achieved slightly higher accuracy of 58%, where the later one has lower Hamming loss of 11%. Hybrid approaches are highly promising since they leverage the scalability of machines over a large amount of data and the quality of human intelligence. While crowdsourcing reduces the cost and latency per annotation compared to domain experts, hybrid approach aim at reducing the overall annotation costs by selecting only the most important instances for being annotated by humans. We consider 2 hybrid techniques: high confidence switching method, as a hybrid method only selects instances for which the machine learning model is uncertain. This method reduces the cost and latency and increases the accuracy when crowdsourcing provides high data quality. The human-machine aggregation is another hybrid method where the predictions of the machine learning model and the inferred crowd answers are jointly combined to resolve the final output. This method aims at combining weak responses to eventually increase the quality of results. This method is useful when latency and cost is not an issue, but accuracy is very important. We have such a scenario with Not-RACE to our platform, which has more than 4,000 volunteers and more than 400 active members. Our proposed hybrid human-machine image categorization is depicted in this figure. This model jointly integrates predictions of a deep multi-input model and inferred labels from multiple crowd judgments. The multi-input model uses visual features extracted from the images and textual features from the metadata, complemented with Wikipedia clauses of concepts extracted in the text. On the crowd answer aggregation, our method considers the workers' reliability scores. This score is based on the performance of workers' task history and their performance in our task. The hybrid approach provides higher accuracy compared to deep learning and crowdsourcing when applied individually. Accuracy achieved is 65% and Hamming loss of 10%. Considering that this is a multi-label classification task with 5 classes, accuracy of 65 can be considered a good number. In summary, in this work we have addressed the task of categorizing images from cultural heritage collections. We presented our hybrid human-machine framework for image categorization. We found that our method of adding Wikipedia clauses of the concepts extracted in the text improves the classification accuracy. Moreover, incorporating annotations from crowd users and applying a weighted aggregation additionally improved the results. In summary, our results have confirmed the assumption that the hybrid aggregation method is an effective approach to combining machine learning with crowd annotation skills. This method is helpful for organizations like GLAMS that maintain data repositories in the cultural heritage domain and which have many active participants. Currently, the Not-RACE to our platform has thousands of registered users and several hundred active participants. Hence, the proposed strategy is well applicable to categorize the images in such a context. We note that on the human annotation part, we expect better data quality with platform members who are residents in the regions where data comes from. The size of the dataset is a possible limitation that especially affects the deep learning approach. In principle, deep neural networks models require more data. Therefore, our future work will focus on increasing the size of the dataset to improve the accuracy. We identified that the collection metadata has additional issues, such as missing high-quality image tags and the period which defines the temporal decade of the images. We plan to deploy our method to also address these additional missing data. Thank you very much for your attention.